Okay, ladies, let's take a look and talk about polynomials today. Polynomials really are just a sum of monomials. Monomials just one term. Polynomials can have many monomials. There are some specific requirements to be a polynomial function. So you have to have a positive integer degree, so the exponents all have to be positive. And then all of the coefficients of your terms have to be real numbers. So that's just looking at the equation itself. Now, if we're looking at a graph, you must have a continuous curve. And it also has to be smooth, which in other words, you have to think about there can be no sharp turns. So let's look at some examples here. So this first one is just an equation of a line. Our function 2x minus 1, we see it graphed. It is, I know it's a straight line, but that's still considered a straight curve. It's smooth, it goes on. You don't have to pick your pencil up to draw that equation of the line. We notice that the exponent here of x is just 1, so that's a positive exponent, a positive degree, and our coefficients are real. Now also, if we look at the second one, we notice that this is a polynomial. If we look right here at the degree of our first term, the degree is 4, right? Because that is our highest exponent of our terms. Now, if you look here, we've got a graph, and you'll notice that if we were going to draw this graph, we don't have to pick up our stylus or a pencil. It is smooth, no sharp corners, no sharp edges, and it is continuous. Okay, but now let's look at some examples of not polynomials. So, not polynomials. So here, if we take a look, we've got the absolute value of x squared minus 6. So it's got an absolute value, and that should already clue in that maybe this isn't a polynomial because it's something a little bit different. And when this is actually graphed, if we look at the graph, we see it is continuous, but do you see how it has these sharp turns right here? So it's not smooth if we look at the overall graph, and so for that reason, it is not going to be a polynomial. Now, if we look at this last one, 2x to the 1/2 power, it does have a fractional power. And remember, I said that you had to have positive integer exponents. Remember, x to the 1/2 is the same thing as the square root of x. And if we look at the graph, it does continue all the way going to the right. However, it stops right there at 0, 0 in this particular case, because we know we can't put in, say, a -1 in for x, because that would end up giving us imaginary numbers. So because this graph has a hard stop and doesn't continue on in both directions, this is not going to be a polynomial. So what I want you to do now is stop and do the first 12 problems for number 1, and then pause the video, come back, and check your answers. Okay, so a couple of things that I want to point out here. You can check your answers here. Some of them were a little bit tricky. I do want to point out number 2, it's not smooth. There are these sharp edges that we turn these corners, so because of that, it's not a polynomial. And also, remember we were talking about polynomial functions. And on number 6, this is not a function. That may have been a little tricky, but this is not a function because it fails the vertical line test. Hopefully you remember the vertical line test from first semester. The other thing I want to point out for number 7 and number 11, we end up having some negative exponents. And even if you just have one negative exponent in your polynomial, that's enough for it not to be a polynomial. And likewise, for number 10, we end up having a square root, which is a fractional exponent, and so that's not going to be a polynomial as well. Okay, so if you need to pause it, check your answers, and then we'll move back to notes. Okay, so now I want to take a look and make a connection between a polynomial and its graph. So the first thing we want to do is look at the overall degree of our polynomial, as well as the sign of our polynomial. And that's going to help us figure out what our polynomial graph is doing at the end. So what we refer to as end behavior. So you'll notice that this polynomial right here is in standard form, which really just means that it's in decreasing order by your degree of each term. So you'll notice that if we look at our first term, we can look at the exponent to figure out the power or the degree. And so we see here that this is going to be a fifth degree polynomial, okay? Now, when we look for in this leading term, again, the leading term just has the highest degree. So we've got this one with the 5. And the coefficient of this leading term is a -4. So that's our leading coefficient. Now we're going to put this all together. So again, the overall degree of the polynomial and the sign is going to be really important to figure out what is going on with the end of the polynomial. So remember, this is in standard form. It's got the highest degree first. Okay, so before we take a look at the chart down below, I do want to remind you, we learned some parent functions first semester. We learned x squared and we learned x cubed. And hopefully you remember the graph of x squared just simply looks like a U. And it's both ends are going up in an x squared graph. Now, if we had negative x squared, all we're doing is flipping it over the x-axis, and instead of both ends going up, now both ends are going to go down. So I want you to notice that in an even degree, both ends are going to go in the same direction. So these are going in the same, so both ends are going in the same direction. Now, if we look at our odd degree, remember we learned about x cubed, and we said it kind of looked like a snake. And looking at this graph going from left to right, we see that it's positive, it's increasing. Now, if we had negative x cubed, we're just going to reflect that. And now, instead of it going from left to right going up, going from left to right, our graph is actually going down. So it just flips. Now I want you to see here that the ends are going in opposite directions. And we'll talk about this a little bit more when we get to this chart over here to the left. So again, I said if you have a polynomial with even degree, both ends are going in the same direction. So let's focus on that. If you have an even degree, so both ends going in the same direction, and a positive leading coefficient, then both ends are going to go up. Here we've got an x squared. This is going to be a higher order, maybe to the third or fourth or fifth power right there. Now, if we end up having a even degree with a negative leading coefficient, then both ends are going to go down. Okay, just like what we saw when we had x squared and then negative x squared. Now, if we look at polynomials that have an odd degree, we've already said that the ends are going to go in opposite directions. And just like we saw with x cubed. So here, if you have a positive leading coefficient and an odd degree, again, your graph is going to be increasing or positive going from left to right, and we see our graph is going up. Same with this example, we've just got a few little bumps along the way before our graph overall goes up. Now, if we have an odd degree and a negative leading coefficient, looking at our graph from left to right, it's going to be going down, okay, or becoming more negative. And you see this in both cases. This appears to be a negative x cubed, and this is a higher degree, but it still is going to be going down. Okay, so now I want you to do problem 2 on your worksheet. So go ahead and pause the video, work on that, and then you can come back and check your answers. Okay, so I'll give you a moment to check your answers. If you need to pause it, you can to check. And then I want to come back and take a look at a few of these. You'll notice in the first one, I did have to reorder my polynomial so that I had my leading term with my highest degree. So this is my leading term right here, -3x to the 7th, which tells me that the degree of my polynomial is 7. And because 7 is odd, that means that my ends are going to be going in opposite directions. But I've got to look at my leading coefficient to figure out which way they go. And my leading coefficient is negative, which means that my graph is going to ultimately look like this kind of reverse snake. Again, my graph overall is going to be decreasing, which means on the left side of my graph, it's going to be going up, and on the right side of my graph, it's going to be going down. Now, hopefully the next two were pretty easy for you to do. They both had even degrees, and so your ends are going to be going in the same direction. Here, we're both going to be going up, and then here, they're both going to be going down. Now, this last one's a little tricky. So here we didn't have everything multiplied out in standard form. We were given the polynomial in factored form. And so when we do that, we actually have to look at our exponents. You don't have to multiply everything out. We can just take our exponents and add them together to figure out what the overall degree is. So we have 2, now this is just raised to the 1 power, even though it didn't specify. So our overall degree here is going to be 3, which means because 3 is odd, our ends are going to be going in opposite directions. Now again, we didn't have to multiply these factors out, but if we happen to, our x terms would end up being positive because it ends up being positive in front of our factors. So we know because it's an odd degree, it's positive. This is going to be our overall shape. Our overall graph is going to be increasing. So the left-hand side of our graph is going down and the right-hand side of the graph is going up. So pause this, make sure you've got everything written down, and then we'll come back and take a look at the next part of the notes. Okay, so now I'm going to introduce a new concept, some that you already know, and a new concept, new vocabulary as well. We all know, we have talked about before, that zeros are a function. We find those. They're really the same thing as x-intercepts. It's just another word. You could also refer to them as roots, x-intercepts, zeros. That's all completely true and accurate. So to find the zeros, we're going to set y equal to 0, and we're going to get our x-intercepts. Now, when we do this, we have to do it by factoring. We have to do it by factoring here. At this point, we'll learn some other ways in the future, but right now we're going to be doing factoring. So here we're given a polynomial that is already fully factored, and we see that there are 3 factors here: x, x minus 3, and x plus 2. And so we want to set our polynomial equal to 0 and solve. And so we're going to set each one of our factors equal to 0 and solve. So we end up finding that x equals 0, x equals 3, and x equals minus 2, and those are referred to as the zeros of our polynomial. These are the zeros of our polynomial, and they're our x-intercepts. We can put those on our graph, and we can go on and graph our function. You see that it's a smooth curve, and we'll talk a little bit more in a moment about how we graph this. Now, that should be a review for you so far, but what's going to be new is talking about multiplicity. This is a new word for you. So multiplicity of a 0, when we have a polynomial that is factored completely, the number of times a factor is repeated gives us the multiplicity, and that gives us a glimpse into what's happening on the graph. So let's look at an example. So here you'll notice that we were given this function. I'm going to erase that right there. We were given this function right here. We already know when we have this x squared that the 0 is x equals 0. But this x is raised to a power of 2, so we say the multiplicity is 2. Now in this next factor, we see that the 0 is actually x equals 3, and this has a multiplicity of 1 because that's raised to a power of 1. And then lastly, we have a 0 at x equals negative 2, and here our multiplicity is 3. So what in the world does multiplicity mean, and why is it important to us? So if you have an even multiplicity, like right here at x squared, what that means is that your graph is not going to cross, it's going to touch. It's going to touch and turn, or you can say it's going to bounce. So at that 0, if you have an even multiplicity, it is going to touch or bounce. Now, if you have an odd multiplicity, your graph is going to actually cross at that particular 0. So what I want you to do now is use this information and go back over to the worksheet and do problem 3. Okay, so I have found the zeros for each one of my polynomials, and I've specified the multiplicity and then whether or not each one crosses or touches. So pause if you need to check your work. One thing I do want to point out is that for this last one, we had to factor it first. We had to factor that polynomial first to find the zeros, and then we could find our multiplicity and whether the graph is touching or crossing.